This is the second video of this series. In the last video, we have discussed variable separable differential equation. Now, today we are going to discuss homogeneous differential equation. A homogeneous differential equation may be defined in two ways. A differential equation of the form dy upon dx is equal to fxy upon phi xy, or dx upon dy is equal to fxy upon phi xy is said to be a homogeneous differential equation if each term of fxy and phi xy is of the same degree. A differential equation of the form dy upon dx is equal to fxy upon phi xy, or dx upon dy is equal to fxy upon phi xy is said to be a homogeneous differential equation if each term of fxy and phi xy is of the same degree. For example, dy upon dx is equal to x square plus 2xy plus y square upon x square plus y square plus 5xy. As you see in the numerator, this is a function of x and y, and in the denominator also this is a function of x and y. So arbitrarily we call it fxy, that is a function of x and y, and we call it phi xy, another function of x and y. Degree of this term is 2. Degree of this term is 2 because there are two variables. So degree of this term is the sum of powers of both the variables. So the degree of this term is also 2. Degree of this term is also 2. Similarly, in denominator, degree of each term is 2. So this is a homogeneous equation, and sometimes it is not written in this form, but you can identify easily by observing degree of the terms. If degree of every term is equal, though that is written in this form or some other form, you can identify a homogeneous equation. For example, x square dy plus y square dx is equal to x square dx plus xy dy. So this equation is also a homogeneous equation because if we observe the degree of this term is 2, because this is x square, power of x is 2. There is y square, so degree of this term is also 2. This is x square, so degree of this term is also 2. And there are two variables in this term, so the degree of the term is the sum of the powers of these two variables. So 1 plus 1, 2. So degree of this term is also 2. So in this way we may easily identify a homogeneous differential equation. A differential equation may also be defined as a differential equation which can be written as dy upon dx is equal to a function of y upon x, or dx upon dy is equal to a function of x upon y, is said to be a homogeneous differential equation. For example, dy upon dx is equal to x square plus 2xy plus 3y square upon x square plus 3xy. So dy upon dx is equal to, we may take x square common out of all the three terms in the numerator. We may write it as x square 1 plus 2. If we divide first term by x square, we get 1. If we divide 2xy by x square, we get y upon x, because one power is cancelled by this x, and plus 3, and this may be written as y upon x whole square, because if we divide this term by x square, we get y square upon x square, which may also be written as y upon x whole square. In denominators 2, we may take x square common, so x square, then we have to divide both the terms by x square. So first term is divided by x square, we get 1 plus, and if second term is divided by x square, one power is cancelled by this x, and we get 3y upon x. This x square is cancelled by this x square, and ultimately we get dy upon dx is equal to bracket 1 plus 2 y upon x plus 3 y upon x whole square divided by 1 plus 3 y upon x. So you see, everywhere we see y upon x, y upon x, y upon x. So this whole expression is said to be a function of y upon x. So dy upon dx is equal to fy upon x, means dy upon dx is equal to a function of y upon x, which is written in this way. So this is also a definition of homogeneous differential equation. Now I told you two definition of homogeneous differential equation. You may take either of these two definitions, whatever seems to be easier to you. Now we will discuss how to solve a homogeneous differential equation. So step 1, first of all, we rewrite the given differential equation, homogeneous differential equation, in the form dy upon dx is equal to f xy upon phi xy, or dy upon dx is equal to f y upon x. Either we write the differential equation in this form or in this form. This is the first step. If it is not given in this form, sometimes it is already given in this form, so first step will be skipped. Now step 2. After that, we assume y upon x is equal to u. Then we transpose x to that side, so we may write it as y is equal to ux. Then we differentiate it with respect to x. So we get dy upon dx is equal to, now we have to differentiate ux by product rule. So u as it is differential of x is 1 plus x as it is differential of u with respect to x is du upon dx, and we make it equation number 3. Then by this substitution and this differential equation, we have to change equation number 1. That is, in place of dy upon dx, we write u plus x du upon dx, and in place of y upon x, we write u. So from equation 1, 2 and 3, equation number 1 becomes u plus x du upon dx is equal to f u. Then step 3, then we transpose u to right hand side, so we get x du upon dx is equal to f u minus u. So in this way, on the right hand side, we get only function of u. After that, we transpose this whole expression to left hand side and x and dx to right hand side. So we get 1 upon f u minus u du is equal to 1 upon x dx, because this x goes in the denominator and this dx goes in the numerator. So we have 1 upon fu minus u du is equal to 1 upon x dx. It is a variable separable form, so further procedure is carried out of variable separable form. That means we have to integrate both sides and we have to find the required solution of the differential equation. But remember, at last you will have to replace u by y upon x. Now let's discuss some of the examples. So first example, y square minus xy dx plus x square dy is equal to 0. So by observing each and every term of equal degree, we can identify this is a homogeneous differential equation. So after identifying this differential equation as homogeneous differential equation, then we have to write it in the standard form. So first we have to transpose this term to right hand side. So we get x square dy on left hand side. This term is left on left hand side and this term is transposed to right hand side. So we get minus y square minus xy dx. Then we have to transpose dx to this side, so it goes in the denominator of dy, and x square should be transposed to right hand side. So we get dy upon dx is equal to minus y square minus xy upon x square. Or we may also write it as, after taking minus common out of these two terms, this minus, we may write it as xy minus y square upon x square. Now the next step is we let y is equal to ux. So let it be equation number 1 and this equation 2. Now we have to differentiate it with respect to x. So we get dy upon dx is equal to u plus x du upon dx. Let it be equation number 3. Now we have to replace y by ux on the right hand side, and on the left hand side we have to replace dy upon dx by u plus x du upon dx in equation number 1. So from equation 1, 2 and 3 we get u plus x du upon dx. In place of dy upon dx we have written this expression is equal to, then in place of y we have to write ux. So here x into ux minus, we have to replace y by ux in the second term, so it becomes u square x square because there is y square. In denominator we have x square only. So u plus x du upon dx is equal to, if you open it up, x will multiply x and you get ux square minus u square x square upon x square, or u plus x du upon dx is equal to, we may take x square common out of these two terms. So x square common, in the bracket we have u minus u square divided by x square. Now simply x square is cancelled by x square from numerator and denominator, and we get u plus x du upon dx is equal to u minus u square. Simply now we have to transpose this u to right hand side, so it will cancel this positive u, because after transposition this u becomes minus u, so minus u and plus u will be cancelled, so we cancel directly. Now on the left hand side we have only x du upon dx, and on the right hand side we get minus u square. So we have to transpose u square to left hand side and x dx to right hand side. So this u square goes in denominator, so it becomes 1 upon u square du, And on the right hand side, this x becomes 1 upon x, and this dx goes in numerator. So simply we have 1 upon u square du is equal to 1 upon x dx. So 1 upon u square may be written as minus u raised to the power minus 2 du is equal to 1 upon x dx. Now this is variable separable form, integrating both sides. So proceeding from this step, integrating both sides, we get integral u raised to the power minus 2 du, u raised to the power minus 2 du is equal to, and on the right hand side, integral 1 upon x dx. So now integral of u raised to the power minus 2 is u raised to the power minus 1 upon minus 1 is equal to integral of 1 upon x is log x plus c. Now you may write it as minus 1 upon u, because u raised to the power minus 1 may be written as 1 upon u, and this minus 1 may be written as a coefficient minus. So minus 1 upon u is equal to log x plus c. You may also write it as log c or simply c. Now no further simplification is left by equation number 2. If we find the value of u, that will be y upon x. So from equation 2, u is equal to y upon x. So write it down, minus 1 upon u, that is the reciprocal of u, that will be x upon y. X minus x upon y is equal to log x plus c. Now let us take second example, that is x bracket x minus y dy plus y square dx is equal to 0. So obviously this is a homogeneous differential equation, because if we open up this bracket, the first term will be x square, that is degree 2, second term will be xy, that is degree 2, and third term is y square, that is also degree 2. So after identifying this equation as a homogeneous differential equation, first we have to make dy upon dx alone on one side and rest of the expression on the other side. So for that purpose, we have to transpose this term to right hand side. So we get x minus y dy is equal to minus y square dx. Now we have to transpose dx to this side and x minus y to right hand side. So we can write it as dy upon dx is equal to minus y square upon x minus y, or dy upon dx is equal to, after taking minus common out of this bracket, we can make this negative positive. So y square upon x y minus x. Let it be equation number 1. So let y upon x as u, or y is equal to ux, equation number 2. Now differentiating equation 2 with respect to x, we get dy upon dx is equal to u plus x du upon dx. Let it be equation number 3. So now from equation 1, 2 and 3, we get, in place of dy upon dx, we have to write down this u plus x du upon dx is equal to, and in place of y we have to write down ux. So in the numerator we have u square x square, and in denominator x as it is inside the bracket, in place of y we have to write down ux minus x. So u square x square upon, here x is common, so we should take x common out of these two terms. So outside there will be x square, inside u minus 1. This x square will cancel this x square, and we get u plus x du upon dx is equal to u square upon u minus 1. Now we have to transpose this u to right hand side. So on the left hand side we get x du upon dx is equal to u square upon u minus 1 minus u. On right hand side now we have to take LCM, u minus 1. So in the numerator we have u square minus u minus 1 will multiply u, so u into u minus 1. Now further simplifying we get u square, open up the bracket, or you may say multiply by minus u, both the terms, we get minus u square plus u divided by u minus 1. This u square positive and this u square is negative, so these are cancelled with each other. Now on the left hand side we have x du upon dx is equal to, on the right hand side u upon u minus 1 is left. Now to make them variable separable we have to transpose this expression to left hand side towards du and x dx to right hand side. So we get u minus 1 upon u, after transposition of u upon u minus 1 it becomes u minus 1 upon u du is equal to 1 over x dx. So now this is variable separable form, so we have to integrate both sides. Integral u minus 1 upon u du is equal to integral 1 over x dx. Now if we split them up we get 1 minus 1 over u du is equal to integral 1 upon x dx. Integrating 1 with respect to u we get u, and minus integral of 1 upon u is log u is equal to integral of 1 upon x log x plus c. Now we have to replace u by y upon x, because final solution should be given in terms of x and y only. So by the substitution we have u is equal to y upon x. So replacing u by y upon x we get y upon x minus log y upon x is equal to log x plus c, and this is your final solution. Though you may write this answer in different forms by basic simplification, as y upon x is kept on left hand side. If you transpose this term to right hand side it becomes log x plus log y upon x plus c, and y upon x is equal to log m plus log n is log m into n, so you may write it as log x into y upon x plus c as it is. This x is cancelled by this x, so you may also write it as y upon x is equal to log y plus c, or you may also transpose x to right hand side, so that will be y is equal to x log y plus cx. So either you write this or you leave your answer here or you leave your answer here. There is no difference. All the three forms of your solutions are correct. Now the example 3 is square bracket x sine square y upon x minus y dx plus x dy is equal to 0. So identification, first term has x, only one variable, the power is 1. So degree of this term is 1. Always remember, if some variables are given in the angle of trigonometrical functions, they will not be considered to find the degree of the term. Degree of the term is taken under consideration only for the algebraic terms. So this is the algebraic term because this is written as the coefficient of sine square y upon x. So degree of the whole term is 1, and here the degree of this term is 1 and degree of this term is 1. So this is a homogeneous differential equation, and now we have to write in the standard form. So first we write as it is, x sine square y upon x minus y dx plus x dy is equal to 0. First we have to transpose this to right hand side. We get x dy, and this term will be minus x sine square y upon x minus y dx, or x dy is equal to, now here if you open up the bracket, this minus will multiply both the terms, and this term will become positive and this term will become negative. So you may also write it as y minus x sine square y upon x, because there is dx operator, so it is better to keep it in the bracket after multiplying by minus 1 dx. Now transpose dx to this side and x to this side, we get dy upon dx is equal to y minus x sine square y upon x. Now dy upon dx is equal to, this x will divide both the terms if we split the terms. So let's do it. X will divide y, we may write it as x upon y minus, if this term is divided by x, this x will cancel this x and we get only sine square y upon x. Let it be equation number 1. So now we have to substitute y upon x is equal to u, or y is equal to ux. Let it be equation number 2. Differentiating equation 2 with respect to x, we get dy upon dx is equal to differential of ux, u plus x du upon dx. Let it be equation number 3. Now from equation 1, 2, 3, we have to replace this dy upon dx by u plus x du upon dx in equation number 1. So on the left hand side, u plus x du upon dx is equal to, on the right hand side, y upon x is equal to u by our substitution, so this may be written as u only, minus sine square y upon x again, that is u. Now if we transpose this u to right hand side, it will cancel this u, because after transposition it becomes minus u. So these two u are cancelled with each other. Now on the left hand side we are left with x du upon dx, on the right hand side minus sine square u. So transposing sine square u to left hand side and x dx to right hand side, we get 1 upon sine square u du is equal to 1 upon minus 1 upon x dx, because minus was there. You may also transpose minus to this side. So if we suppose if we transpose this minus sign also to left hand side, so this minus may also be written here on the left hand side, there is no problem. Either way you can do this. So minus 1 upon sine square u, it becomes minus cos sec square u du, because 1 upon sine square u may be written as cosec square u, so we have written this as minus cosec square u du. Right hand side 1 upon x dx. So now it is variable separable form. So integrating both sides, minus integral cosec square u du is equal to integral 1 over x dx. So as we know, the integral of cosec square u is minus cot u. So that minus cot u, the integral of cosec square u, and is equal to, this is 1 upon x dx. So integral of 1 upon x is log x plus c. Opening the bracket, these two minuses become plus. So cot u is equal to log x plus c. Let it be equation number 4. Now it is not our final solution, because as we have observed in this example, a boundary value condition is also given. So if a boundary value condition is given, that means we need to find the value of c also. So using boundary value condition, y1 is equal to pi by 4. This value indicates the value of x and this value indicates the value of y. So it implies that when x is equal to 1, y is equal to pi by 4. Now putting the values of x and y, but before putting the value of x and y, we need to change this u in terms of x and y, which is y upon x. So we write cot y upon x is equal to log x plus c. Now putting x is equal to 1 and y is equal to pi by 4, we get cot. Now we have to substitute y is equal to pi by 4. So pi by 4 and x is equal to 1. So putting y is equal to pi by 4 and x is equal to 1, we get cot pi by 4 here, and log 1 plus c. So as you know, cot pi by 4 is 1 and log 1 is 0 plus c. So it implies that c is equal to 1. So finally we found the value of c that should be written in equation number 4 to find a particular solution. So putting the value of c in equation 4, we get cot y upon x is equal to log x plus 1, and that's your final solution. So here I have given 3 examples to make you understand better. I hope you have understood the concept. Now I would like to say few words about the second form, which I told you initially, that you may also write the homogeneous differential equation as dx upon dy is equal to f x upon y. If there is dx upon dy, then the function should be written in terms of x upon y instead of y upon x. So there is no difference in these two forms, except a very small difference, and you can understand algorithm is same. Just you will have to keep in mind, then in this case where you have made dx upon dy and on the right hand side f x upon y, here substitution where you take y is equal to ux, instead of this substitution you will have to take x is equal to uy, and then you will have to differentiate this with respect to y, not with respect to x, so that you get dx upon dy on the left hand side, and on the right hand side u plus y du upon dy. Then you will have to replace here dx upon dy by u plus y du upon dy, and here x upon y by u, because now substitution is x is equal to uy. So the value of u by this substitution will be x upon y, so that will become fu, and rest of the steps are the same. So you may also adopt this method to solve a homogeneous differential equation.